Welcome to LNP Renewable System Regulator. Today we are going to discuss the basics of pressure transmitters part 2. Okay, we had already discussed a few more basics regarding this pressure transmitter in the part 1. If you have missed it, we had provided the link in the description. So by referring that link, you can be able to understand the topics that we had discussed in the part 1. Now let us get into the topic of part 2. So what are the things that we're going to install? Okay, how a pressure transmitter is installed, okay, how a pressure transmitter works, and what are the things as a building management system engineer or BACS engineer we should know in the pressure transmitters. So how it is installed? If you have a flange tap settings, okay, across the heat exchangers, if you're planning to install a pressure transmitter, so we need to connect one of the end on the flange tap flow side, and the other tap side also we need to connect our pressure transmitter. So this is how basically we need to install the pressure transmitters, okay. And as we told earlier, in the chiller water systems and the heat exchangers, we can use this. So we can see here we have a PDITs, that is pressure transmitters, which is getting installed across the heat exchanger 1, 2, 3, 4, 5, okay. So, and even see here in the pump side also we can install this pressure transmitters. So it is a very useful device. Even for we can find out the pressure difference between the supply and the return line with the help of these pressure transmitters. So how it is installed? So the first model is that if you are going to install your pressure transmitter in a open vessel, so this is how you need to install. Okay, for all the things the formula is going to be the same. Okay, if you want to calculate the start of a scale value, that is density into gravity into lower filling level. Okay, this lower filling level, this is the lower filling level. Okay, this is how we need to calculate the lower filling level of an open vessel. Okay, if you're going to calculate the full scale value, that is the density into gravity into we need to multiply the upper filling level. So this is how basically if you're making any sort of installation calculation for a open vessel, okay, this is how you need to install, and most importantly you need to have a flanges for the better installations. Okay, next model is that if you're going to install, okay, your pressure transmitter in a closed vessel, okay, where the gas is getting filled, in such places you need to install like this. Either you can install here or you can install here with the help of these flanges across these two heads, okay. And the formula is going to be the same, okay. So this is how you need to install a, if you're using, if your application is a hydrostatic level measurement, if it is a closed level, then you can use this methodology. And the third type is that if you are installing in a closed container where there is a possibility for strong condensate formation, that is if you are having a constant compression level, okay, and you're going to increase, we have a different valves, okay, you need to come across a gas filled compression chambers. In such places you need to install like this. And how it works? So as we know earlier, it has so many electronic components in it. We have a sensor, okay, we have an amplifier, we have an analog to digital converter, we have a microcontroller, we have a digital to analog converter, and we have an EE probe. Okay, this is an example. We got represented as the Siemens pressure transmitter. This is a basic example we had provided. So the basic function of this sensor is to measure the physical change which is happening inside the container or inside the tube where we are going to connect this pressure transmitters. And so once it gets the electrical signal, with the help of this amplifier, it amplifies the electrical signal. Then we will send that amplified electrical signal to the analog to digital converter, because we have a microcontroller inside. So microcontroller will understand, will receive only the digital signals. So in order to make the microcontrollers to understand it clearly the signals, so we are converting the analog signal to digital converter. So the microcontroller will be there, and microcontroller will do its job. So it will display the settings, everything it will do. So from the microcontroller it will go to the digital, exact precise output the microcontroller will produce. From the microcontroller it will go to the digital to analog converter, because we need an electrical output also. So even for displaying purpose, we are doing this analog to digital conversion, and the microcontroller, which will process it and it will display. In the LED display, we'll have a precise value, the exact value of pressure that we are having. But after that, with the help, we need to monitor this in the PLCs and the distribution control systems also. So for that, what we need to do, we need to convert this signal that we are getting from the microcontroller to digital to analog converters, and final output we will get a 4 to 20 milliamps output. And inside that PLCs or DCS, we will have a functional blocks. Inside the functional blocks, we used to do the scalings. So this is how basically all these things will work. Okay. And most importantly, if you want to get a electrical output, if it is in the current form 4 to 20 milliamps, you need to give the auxiliary power for its operation. And if you go in depth in installation, we have so many varieties. So if you plan to install a pressure transmitter above the measuring point, this is how you need to install. We have only one flange. Okay. If you plan to install the pressure transmitter below the measuring point, this is how you need to install. Okay. And if the flange is at the top, okay, then with the help of this third method, type C, we can install like this. Okay, but we need to calculate each and everything in order to do the scaling value. In order to find out the scaling value, the formula is getting different here. Okay. And if you have two flanges, okay, and you plan to install below the lowest flange, you can use this method. Okay. And if you plan to install below the lowest measuring point, you can use this method. For that, we have a different formula. You can use this formula and you can easily able to find out the things that you need. And if you plan to install above the upper measuring point, then you need to use this method. Okay. And if you plan to install between the two measure points, then you can use this method. But for each and everywhere, we have a difference in formula. Make a note of it. So as we know earlier, how it is electrically connected. So as we know earlier, this we have a analog to digital converter, which will go to the microcontroller. From the microcontroller, it will go to digital to analog converter. So what will happen? We are getting electrical output. So if we connect our cables, the PLC cables, that is our analog input cables and the analog output cables in the 1 and 2 terminal. See here, we are providing the auxiliary source here and we are getting the electrical output. So from 1 and 2, we can get our required electrical output signals. So this is how basically the auxiliary power will be provided to these pressure transmitters. So see, as we saw earlier in the loop drawing in the part 1, normally we used to connect the pressure transmitters if it is located in the remote locations. If you want to connect it with the PLCs or the DCS, we need the help of these junction boxes. Okay, see here how the signals are getting transmitted, 4 to 20 milliamp signal. So it will go to the junction box. From the junction box, it will, with the help of this code cables, we used to transmit it to the DCS and the distributed control systems on the PLCs. Say for example, okay, if there is no flow and we are providing electrical signal, so what will happen? We will get a minimum output of 4 milliamps. So we need to scale this 4 milliamps to 0. So this is how we need to do the scaling inside the PLCs. Okay, so PLC card, we are providing the signal of 20 milliamps and we will get a feedback signal of 4 milliamps if there is no flow. If there is a 50% flow, okay, we will get an output of 12 milliamps. See how it works. So we are providing 20 milliamps. So that is a 50% flow. So we are getting a feedback of 12 milliamps. So this is how a basic pressure transmitter will work. So we have a 100% flow. Okay, so we are providing 20 milliamps. The entire output we will get. So how this? So we can use this flow transmitters as a pressure transmitters also. So as we said earlier, if you want to measure the flow, you can use these. Okay, and if you want to measure the pressure, you can use this. For both the purpose you can use, but the basic working functionality is this. Okay, If in the same place, instead of this flow, if your pressure range is 0, your output will be 4 milliamps, and if your pressure range is 50%, your output will be 12 milliamps, and if your pressure is 100%, the maximum limit, then you will get a 20 milliamps output. Okay. So we can scale these pressure transmitters. Okay, with the we are connecting it to the PLC. How scaling is done? We might have a doubt. Say for example, consider we have a pressure of 0 to 100 bar. Okay, see here. So now we are categorizing the pressure range in percentage: 0, 25, 50, 75, 100%. So for 0%, the pressure will be 0 bar, and the electrical output will be 4 milliamps. And for 25%, it will be 2.5 bar and 8 milliamps. For 50, it is 5 bar and 20 milliamps. Okay, and if it is for 75%, the pressure range will be more, the electrical output will be more than the normal one. See here, 5 bar is, so if it is 75%, 7.5 bar is 16 milliamps. If it is 100%, it's 10 bar, that is 20 milliamps. This is how we need to do the scaling of the electrical value with the percentage. This is how basic scaling will be done.